Let's take a look at, generally we've set up a lot of stuff before this, but we're going to look at solving exponential equations. Some of these things we have seen before, and we're just going to kind of go over again so that it's fresh in your mind. So, first method, I've kind of split this out into different methods depending on what you're seeing. Writing using a common base. We should be able to look at this first problem and see that 3 and 27 are both powers of 3. So writing this, leaving this as 3 to the 2x plus 5, and writing this as 3 cubed to the x minus 2 should be able to make us write this as 3 to the 2x plus 5 equals 3 to the 3x minus 6 when we distribute that 3 through there. And now technically what we're doing on this particular equation, okay, I'm going to bring that back up here, is we are going to take a log base 3 of both sides. Okay, so we separate these things out a little bit so I have some space to put that in there. Stick those back together. So we're going to take a log base 3 of 3 to the power there, and we're going to take a log base 3 of 3 to the power there, because the inverse nature of those operations is a log base 3 cancels out what a 3 to the power does. And so the power comes down, right? Just like our property said, now that we see an exponent inside of the logarithm, the 2x plus 5 comes down. It leaves us that times, technically still here, a log base 3 of 3 is equal to the 3x minus 6 that comes down times the log base 3 of 3, but by our properties, log base 3 of 3 is just 1, and so we have this equation that looks like 2x plus 5 is equal to 3x minus 6, and so x is equal to 11 after a little bit of algebra. Let's see, I'm going to shrink this stuff all down a little bit so it's not interfering with my next problem. It's the same effect as when we looked at this over here before and said, it's 3 to a power on both sides, so the powers must be the same, and that argument leads us directly to that point. But we're going to show that it's valid in terms of the properties of logarithms as well. All right, our second one here. We're going to take a look at solving 72 equals 10 to the x over 2 plus 5 power. Okay. See if we can see that a little bit better. All right, on this one we see a 10 to the power on one side, so we're going to get rid of that or we're going to change the form here by changing this from its exponential into its logarithmic form. And so normally y equals b to the x, right? That's what we're thinking here. So this is the y, the 10 is the b, this whole thing up here is the x, and in its logarithmic form, it is the log base b, mathematician shortcut, the base is 10, I don't have to write it. This will be that the log base b of y is equal to x over 2 plus 5. Or not log base b of y, sorry, my y is 72, so it's log of 72 is equal to that, and now that's a button that I have on my calculator. So I'm going to go to my calculator and I'm going to say, hey, what is the log of 72? I don't actually have a voice activated calculator, I had to type it in. And it tells me that's about 1.8573. I'll keep about that many decimal places. It is equal to x over 2 plus 5. So subtract 5 from that, and I get negative 3.1426. Can't go more than 4 decimal places based on what I had there. 7, coincidentally close to pi. That was purely an accident. is equal to x over 2, a happy little accident, and x is equal to negative 6.2853, approximately. We'll go with approximately there because we definitely did some rounding there, so what we'll be looking for in the exponent there was about a negative 6.2853. Okay, so that's great if we have a base that happens to correspond to the button that we have on our calculator, but what if we don't have a calculator with a base 3 button that we're looking at here? There are some calculators that do, but they certainly don't all have that. So let's go ahead and just use the logarithm that we do have. So we're not changing the form here necessarily. What we're going to do is we're going to, as long as we do the same thing to both sides of the equation, we should be all right. So we're going to take a log on both sides. We'll do log 72 equals log of 3 to the x over 2 plus 5 power. Okay, well, what does that do for us? Well, we know that the log of 72 from before, or using our calculator again, is about 1.8573. On this side, we now have this thing in the exponent of a logarithm, so it can come down, and we'll bring the x over 2 plus 5 down in front there, and then that's times the log of 3. Okay, so we've got 1.8573 equals x over 2 plus 5, and the log of 3 is, we can figure that out too because we have that button on our calculator. Log 3 is about 0.4771. And so we can, let's go ahead and divide both sides by 0.4771. This is a linear equation now. We've been doing these for years. So I'll go to my calculator again, 1.8573 divided by 0.4771. And I get a 3.8929. Is equal to x over 2 plus 5. Now I'll subtract 5 from that again and multiply by 2, and I get x is approximately equal to negative 2.2142. Okay, no big deal. We can do that. Let's see. This one I'm throwing in here because sometimes there is some work that you have to do ahead of time before you can apply things. I mean, we could apply a logarithm on both sides here, but most people would forget that there's this other multiplication that's happening in here. So it's always best if you can get it to look more like a y equals b to the x form. So we can start that process out by dividing by 100. In fact, what I'm going to do is I'm going to demonstrate this one with an arrow diagram because I haven't done that in a little while. So we start with the t. It is multiplied by 12 first, and then that goes into the power of 1.075 raised to the power there. And then we are multiplying by 100, and we're supposed to end up at the end with a 200 as an answer. Okay. Well, we know we've got to work our way back to the t here. So the opposite, the inverse operation to multiplying by 100 is dividing by 100. The inverse operation to 1.075 to the power is, by our change of base formula, log of that thing divided by the log, base 10, common log again, of 1.075. Okay. We could solve this problem by dividing by 100 on both sides and doing it just like the previous problem, but I wanted to show this one along the way as well, and then this is going to be divided by 12. So this part in here, again, the first time in a video that we've written this down, but it's combining two steps. It's taking the log base 1.075, but we don't have a 1.075 button on our calculator, but our change of base formula says we can change it to any base that we want. So whatever it is that we happen to be taking the base of here, 1.075 to the 12t power, okay, which the 12t would come down and leave us asking what is the log base 1.075. Well, on the other side we have a 200 or something there. So, but this inverse operation there is, again, 1.075. We're changing that with the change of base formula into the log of something divided by the log of 1.075, the old base. So that's what our change of base formula looked like, and that's what we're doing right there. Okay. All right, so with that explanation in place, let's go ahead and follow this thing back. We started with the 200, and it said the first thing you should do at 200 is divide by 100. That'll give us a 2. Okay, and then we want to drop that 2 in the empty set of parentheses, so it's going to be log of 2 divided by log of 1.075. And once we get an answer out of that, then we're going to take that whole thing and divide it by 12, and that should give us our approximate value of t. So I will put that into my calculator. Log 2 divided by log of 1.075. Get an answer, divided by 12, and I get about 0.7987. And that is my answer to that one. All right. We double check some things there. All right, and then finally, sometimes the stories, and we worked on this before, how to kind of write these stories from the descriptions. So we've got a chemical that gets spilled in a lab. The ventilation system is able to filter out some of that. In fact, it can filter out half of what is in the air every 8 hours. Initially, from the chemical spill, we've determined that there are 1,300 parts per million of the chemical in the air. That's how they measure these kinds of things. The safe level, however, is 20 parts per million. We want to know how long are they going to have to wait before the scientists can go safely back into the lab. All right, so let's see what we've got here. Initial is important. That's our starting value, right? So we got 1,300 parts per million initially. We're able to remove, through the ventilation system, half of that. So after 1 hour, well, after 8 hours, we'd be down to 650, right? So that means this needs to look like a t divided by 8 up here. So when we put an 8 in there, we do 8 divided by 8 is 1, and we multiply by half one time, and it's down to the 650. After 16 hours, if we put a 16 in for t, 16 divided by 8 is 2. That's going to multiply by half twice and continue with our filtering process there. And we want to know how many times do we have to do that before we get down to 20 or below. So I guess technically we want to know when this will be less than or equal to 20. But we'll solve it just like it was an equal sign. Okay. We'll do this one different than we did the last one. So, I mean, we could do arrow diagram again, or just show More traditional methods for this. It's going to start by dividing by 1300. There's a little bit of, I can see that's 1/65th is equal to 1/2 to the t over 8 power. And now I've got to get this t down someplace where I can work with it, and the logarithm is the tool to do that. So I'll take the log of 1/65 is equal to the log of 1/2 to the t over 8 power, which of course is going to give me, well, log, I'll leave it as this and put the numbers into my calculator at the end. Log of 1/65 equals t over 8 times the log of 1/2. And now we get the t over 8 down where we need it. We need to get rid of this 8, obviously, and the log of 1/2. So I'm going to do the log of 1/65 multiplied by 8, divide by the log of 1/2, and that should give me my value of t. It's actually not approximately equal to in this case. It's exactly equal to, but by the time it's gone through my calculator, it will be approximately equal to. So log of 1/65 divided by the log of 1/2. And I get t approximately equal to 48.18, 48.2, and this would be in hours. Everything, my units were all in hours, so it's going to be a little over 2 full days for the system to filter enough out that it's safe for the scientists to go back in.